Welcome to Breadboarding. This is video 33 in the Breadboard 8088 PC series, and PC compatibility part 11. We'll be looking to try and boot an early version of DOS from floppy disk. Now, in the previous couple of videos, we've been going through testing a number of the systems that are highlighted there in green, but when we came to test the DMA controller, that is the direct memory access controller, that was failing. So what I've got now is I've got some new chips come in, and I'm just going to summarize what was going on there. And what we're going to be trying to do at the end of this video is booting up an early version of DOS. So in fact, it'd be PC DOS 2.1 from IBM. So in the previous video, we had two DMA controller chips, so 1980 AMD chips, and they appeared to have a fault with some of the data lines. So the D1 and the D5, D6 data pins on the two chips seemed to have problems. So Sergey Kislev had recommended on another forum chat about using the Intercell 8237A chips, and these are more recent. I've bought a number of new ones of these and I've tested them out. So I'm going to test these chips in NetProm Programmer, and I have done some tests for that. So I'll just quickly show you those. So for the DMA controller chips, what I've done is I've mapped out some tests here, and these tests have then been put into the XG Pro EPROM programmer software, and then being able to actually test the various EPROMs. So this is basically just putting in various test patterns, so from null zeros, AAs, and various other sort of patterns, just to see whether we can save values to the registers and then read them back. So then configured these into the programmer. So in XG Pro, I've created a P8237A test here. If we have a look at those, you can see we've got the pinouts here and that matrix I've put in there. So that's all been put in here. And what we're just going to do is to put one of the original 1980s chips in the programmer and just run the test. So this is the AMD 1980 DMA controller. It's in there. So I'm just going to test that. Hit test, and we can see that a number of the tests have actually failed. If you look over here, you can see there's L's and H's are really here where we're expecting lows and highs, and where they're in red, then it means that the test has failed. So I'm just going to swap out one of the other old ones I had and just test that as well. And we can see now that this has actually failed with some different values here. So different tests have failed here. So this is one of the reasons why I wasn't having much joy trying to get the DMA controller to work. And then I've got one of the new Intercell ones, and I'll just test one of those. That's in the programmer. Just going to run the test now, and that all appears to have passed. So there definitely was a problem with some of the original DMA controller chips. Don't know if I've caused it or if they're faulty before I received them. But anyway, the replacements have arrived, and I've got quite a number of those. So let's have a look at the other issues I had with DMA controller. So you can see we've tested the chips. The old ones fail, the new ones pass. But I found out I still needed the DMA sort of X-bus data bus between the DMA controller and the A8 to A15 latch. I did try removing that, but the instability returned. So I've still added that. I'll cover the details of that in a later video. And I've also repeated one of my DMA tests, DMA test 1, and that now works, and I'll just show you the results of that. Okay, so we're just going to run the first DMA test program I did, and I covered this in more detail in the previous video. There'll be a link at the top of the screen if you want to go and have a look at that. And all this does is fills an area of memory. We're starting at the segment 5000, and then at 7800 we're just going to put 512 bytes, which will go from 0 to FF and then 0 to FF. So that'll be filled there, and then what we're going to be then doing is using the DMA controller to copy that block of memory at 7800 up to 7C00. So I'm just going to download the program, and then we'll have a look at the memory in the nanocomp. So I'm just powered on the nanocomp, send down the test file. And if we now just have a look at the display, you can see that has finished. I'm just going to go to the 500 segment, so I type E for the extra segment, 5000. So that means whenever I do any memory addresses now, it's in that 5000 segment. And we're just going to have a look at 7800 to start with, and you can see I've got FA, 88, 8076, 76, so there's random data there. And if we go to 7C00, again we've got pretty much random. What we'd expect to see there is 0, 1, 2, 3, 4 going up to FF. Okay, so we're just going to go back and set up the logic analyzers. So I'm just going to run that. We've then also got the other one, which is monitoring the address bus, data bus, and is also triggered on the address strobe there. Just going to run the test program. Okay, and we can see that that has run. If we zoom in here, we can see initially we're writing some values to the DMA controller. We can then see that there's a period here where the DMA controller has requested control of the bus, and then shortly afterwards, you can see after just a couple of bus cycles here, gap between these two parts here. So you can see that after about 500 nanoseconds after requesting the bus, then it gets the bus. And then we can see that the DMA enable goes low, so that means the DMA controller has control of the bus. And we can also see that the AMBRD goes high, so that means that the CPU is no longer controlling the bus, so that's good. And then we can then start to see that we've got lots of these address strobes. So we'd expect to see for each of the bytes being transferred, we'd see the address strobe for the source address and then the destination address. So if we actually just put in the timing markers here, so that's at the beginning, and we put a timing marker at the end. And then if we look at this channel here, we can see that the pulse counter, there's 1024, so that's exactly what we'd expect. So we are doing 512 bytes, and then we can see that the TC value goes high. That indicates to the device that was requested DMA that the whole transfer is completed. DMA enable goes high and the CPU takes over. So that should indicate that everything is working okay. Then if we have a look at the other DMA, so we can see that when the address strobe starts, what we were seeing before was when we get the address strobe, we have 78 in the data bus, and that then gives us an address of 7800. We're then getting the next address strobe of 7C, and that's giving us 7C00. Now what we were finding previously where we had the old chips that were causing problems is that this would work okay for a couple of transfers, but then you started to get stray bits all over the place. We can see here that this is going 7801, 7C01, 7805, C05. So this actually appears, if we zoom along, so if we get to 7C17, 7817, so this actually looks like it's working better. And also we can see here that when we're reading 7817, we're reading the byte 17, and then we're writing that byte as well. So we can actually see that this looks a lot better. What I'm just going to do now, we're just going to look at the nanocomp and actually inspect the memory addresses. Okay, so again, we're just going to make sure we're looking at the right data segment, 500. Now I'm going to look at 7800. And we can see at 0, 1, 2, 3, 4, 5, 6, 7, 8, going all the way up. And if we go to memory 7, 8, F0, we've got F0, F1, F2, F3, F4, F5, F6, all the way up to FF. And then it goes back to 0, 1, 2, 3. So that looks like the source address is all correct. Now if we go to 7C00, again we've got 0, 1, 2, 3, 4, 5, 6, 7. That's good. If we then go to 7C F0, F0, F1, F2, 7D F0, we can see now that in fact it has filled. If you get to FF, then that should have filled the entire range we wanted. Great, and then that's just random data. So it looks like the test has completed properly. So it did look like it was those old 44-year-old DMA controller chips were a bit flaky, and certainly this looks like it should have a better chance of working now. So these initial DMA issues seem to have been resolved. Then I had some other problems, so I also found that the programs were not continuing after DMA, they were not continuing the expected place, and this was caused by the fact that DMA weight from one of the PLDs was not actually being output. And if we have a look at the win merge of the changes I made to fix that, you can see here I'm comparing the original PLD configuration, and we've got the fixes on the left and the original on the right. And what I've also done is added the DMA chip select in here for a separate issue I'll talk about in a few minutes. But then what the actual problem was if you look on the right here, the slash here was missing. This meant that the DMA weight was not actually defined as an output. And when looking at the documentation file for these, you can see that DMA weight had no pin assigned here. And if you look at the documentation for this one, then pin 17. So that was a fairly simple fix, but it took a while to get to the bottom of. I would recommend you always have a look at the documentation files just to check that all these definitions are there. The other thing I came across is that the Western Digital chip that we're using doesn't actually, in the DIP, in the DIP breadboard form, doesn't support the pin needed to support disk change, and so the BIOS was expecting to have that value, so the BIOS needed modifying to ignore that. And you can see down here, it's an excerpt from the data sheet, that when it's in DIP then there's no pin there, when it's in the PLCC version then there is a pin and the disk change enable there. So what I'll need to do is to modify the design a bit and be able to do some separate logic for bringing in the disk change. I also reconfigured the BIOS to use the full 512K of RAM that we've got there. When we were debugging this, I was loading the BIOS into the upper area of RAM so that I could do a fair amount of testing, but now that it's relatively stable, I've burned that into EPROM. I've also added quite a bit of output to the power on self-test port for floppy disk access so I can debug that. And the Nanocomp monitors actually had quite a lot of enhancements to better work with the BIOS so that the interrupt vectors, non-maskable interrupt and register display can all be used to help debug the BIOS. And in fact now the monitor's been integrated with the BIOS, so it comes up in the Nanocomp monitor, and if you press B now then it will go in and automatically boot the BIOS, so it makes it much easier for testing the BIOS. Now it's worthwhile having a quick look at the memory map for this because it gets quite tricky when trying to work out what's going on here. We've got 1 megabyte of RAM going from 00000 at the bottom all the way up to 5Fs. So I'm not showing as the segment as a separate thing because it just, I think, confuses things. So what we have is the first 256 bytes are the interrupt vectors. Now the main ones which are used are 0 to 1F, and there's also a few used for the second interrupt controller between 70 and 77. Then the BIOS actually uses a stack starting at 400 going downwards. So in fact the early parts of the BIOS use a stack actually working in this area. Then there's a BIOS data area where there's quite a bit of information on the status of the BIOS floppy disks, things like that. Then as part of the boot process, what happens is the floppy disk boot record gets loaded into 7C00 up to 7DFF, so this is 512 bytes, and as part of the startup of the operating system it loads the root directory, first sector of the root directory at 500. io.sys, which is one of the MS-DOS files, gets loaded at 700. Then as part of that then I think MS-DOS.sys then is loaded at 8000. So as part of the whole boot process, this is actually quite a lot of complicated stuff that's going on behind the scenes, and when it all works it's absolutely wonderful, but trying to get to the bottom of why it doesn't work has been quite a challenge. Now the actual RAM area we have is actually the lower 512K of address space. We then have our video controller, the monochrome display adapter is at the B000 range, and then the BIOS and the monitor are now in the top 32K, so this is F8000, and the Intel 8088 and 8086 processors, when they come out of reset, then they actually look to execute instructions starting at the FFFF0 address. So at the moment what I've done now is, rather than starting the BIOS, what this now does is goes into the monitor waits for a B for BIOS, and then it kicks off the BIOS. So it's made it a bit easier to debug some of the problems that have been going on here. Now what actually goes on when the PC starts up is the BIOS does lots of testing, initializing and things, but in fact to actually boot the operating system there's an interrupt called interrupt 19 which boots the operating system. In fact in the XI8088 BIOS there's an initial program load function or procedure, and what this will do is retry booting off the floppy disk up to 4 times. It resets the floppy disk system, it then gets some drive parameters and things, which again I'll talk about in more detail in later videos when we go into this in more detail. What it then tries to do is to read one 512 byte sector off the floppy disk drive using head 0, drive 0, track 0, sector 1, and it loads that into the 7C00 range via DMA. Now that is the floppy disk boot sector, and the floppy disk boot sector will actually be loaded between 7C00 and 7DFF, and then what it will then do, check the boot signature, so there's a magic number at the end of the boot sector with AA55, which is like alternating ones and zeros in two different patterns, and then if all that passes, it then jumps to 7C00 where the initial part of the operating system loads. So one thing to note is a floppy disk boot record is different from a hard disk master boot record. The master boot record on a hard disk allows a number of partitions to be defined and works out how to boot which partition, but the floppy disk boot record is operating system specific. Now the floppy disk boot record, there's a whole site, Starman PC Ministry, which I'll just show you a quick glimpse of. I'll include the links in the description below the video. And so this URL here has a detailed overview of how the MS-DOS 5 floppy disk boot sector works, including quite a lot of decoding of all of the code that actually runs as part of that. Now, I'm trying to use initially MS-DOS 3.3, so that doesn't really cover it here. So what I've done is my own analysis here. Now, I'm not going to go through all the details of this here, but just to show that this is actually the boot record. So this is used Norton Utilities to look at the boot record, and you can see that in the text over here, there's something here that says this is the OMID, so MS-DOS 3.3. You can see down the bottom, in fact, we've got io.sys and msdos.sys, the two of the files it looks for in the root folder. And you can also see there's a couple of the messages here, so non-system disk and disk boot failure. So if you ever see a non-system disk or disk boot failure, then that is actually coming from the operating system boot up. And I have done a similar diagram for MS-DOS 3.3 as Starman has done on his site, and I'll go into this in more detail once I've actually got to the bottom of booting MS-DOS 3.3. And I also came across an issue where it's possible to have the DMA enabled and also to be writing to the DMA controller chip at the same time. And what this was actually causing, I was seeing that sometimes under some of the testing I was doing, that the address 7C00 would be reversed and it would be 007C, and this would result in overwriting the lower area of memory and all sorts of bad things happen. So this diagram here is actually looking at both the DMA enable and the DMA chip select, both are active low, and where we have zeros here, this means that both of them coincide. Now this is not a good thing, and I looked into a little more detail, and the site that I showed here, this is Adventures in PC Emulation. This is actually a good analysis of DMA, and what I noticed here is that this is the diagram from the original PC XT schematic diagrams, and this I recognise, but there's this extra bit here which has the IO write and the DMA chip select actually coming in here. And so I looked into this a little bit more, and needless to say, the documentation that IBM provided, there's a difference between the 1983 version and the later version. So this is the version we've been running from, and you'll see here that we have the lock S0, S1 HQ DMA signals coming in here. But in the later version from March 1986, you'll see that there's this orange bits here that we actually need. And if we zoom in there a little bit more, so what you can see here is what this logic here is actually doing is this is preventing DMA from being enabled if there are writes going on to the DMA controller at this point in time. So what this effectively does is waits until the writes have completed before it's able to actually start the DMA. Now this, I think, was actually the cause of the problems I was seeing occasionally that was actually stopping things from booting. Sort of done to work around that. Again, the PLD configuration I was showing a little earlier. We've now added the DMA chip select in here, and the conditions for the DMA enable. You can see here that the request DMA, which previously had the S0, S1 lock and HRQ DMA, this now includes a condition which includes the IO write and the DMA chip select. So basically, if IO write and DMA chip select are both low, so that means there's active configuration of DMA controller, then it will prevent it going to request DMA mode. So that seems to have actually stabilized things quite a bit. So now, having repeated this test after that update, then you'll now see that the times where we get DMA enable and DMA chip select has now actually disappeared, and this problem I was seeing where the 7C00 was being reversed has been eliminated. So now we're going to have a look at booting up PC-DOS. So I have been working with MS-DOS 3.3 for most of the time here. However, I did find that PC-DOS 2.1 would actually start up more reliably than MS-DOS 3.3 at the moment. So what I'm just going to do is to show you the PC-DOS booting up. Just going to try and boot. Press B on the Nanocomp keypad to start the BIOS. Get the power on noise. Memory testing. So the floppy disk was whirring away there. Now we've got the date. Now, because there's a real-time clock, we need to put in today's date, which will be 05/07/2024, and the time is 1951. And there we have IBM personal computer DOS version 2.1. Now at the moment it doesn't do very much, it hangs now at this point, but we have been able to boot the PC-DOS version 2.1 here, and what I have been doing is doing lots of logic analyzer analysis, and I will be looking at that over the coming weeks, and hopefully we'll be able to get not only PC-DOS 2.1, MS-DOS 3.3 working as well. Okay, so there we have it. We've been able to boot DOS, IBM PC-DOS in this particular case. I'm going to be looking a little bit more detail at the MS-DOS 3.3 boot process. I've got lots of diagnostic information, and what I'll also be looking at, within the last week, Microsoft have actually released the source code for MS-DOS 4. They previously released earlier versions of DOS, but MS-DOS 4 is actually quite a bit more useful, and they've also included a lot of the F-disk format and the boot sector and the sys and IOSys source code as well, so it's possible to build the entire operating system, whereas earlier drops they didn't include necessarily all of the bits that you needed to build a bootable floppy disk. So what I will be planning to do over the coming weeks is to actually build my own version of MS-DOS 4, and all I will be doing is looking at adding in some sort of debugging support for sending information out to the post port and things like that. We've managed to get pretty much to the end of building the basic floppy disk PC. We've got a little bit more work just to get MS-DOS 3.3 to boot cleanly, and it may very well be that by building MS-DOS 4 from source we'll actually be able to get a lot more diagnostic information about what's going on in the internals. So I'll be looking at that over the coming weeks, and in the coming series of the project what I'm going to be doing once I've got the full DOS working reliably, we'll be looking at building out the real-time clock, an IDE disk controller, seeing if we can boot DOS from the hard disk. Then we'll be enhancing the video controller to do CGA and MCGA, looking at getting the mouse running, and then hopefully trying to run an early version of Microsoft Windows. So that will be coming over the coming months. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, it just helps to make the videos available to a wider number of people. Thanks for watching.